Good evening friends, this is a short video on how to draw graphs on Smith chart. Subject is microwave and radar engineering. Topic is impedance matching and subtopic is parallel stub matching. In previous video we saw how to draw series stub for open circuit as well as for short circuit. I will show you that golden rule again. If it's a parallel stub, it's 0.25 on the graph, which is on the right hand side is short circuit, and on the left hand side it's open circuit. So let's do this. The ZL is given as 100 plus J100, the characteristic impedance as 50, and it is a single stub parallel short circuit. So I'll just write in gist that it is a parallel short circuit stub. So I've just drawn a small diagram. For time being, just forget it. Just watch what Y stub is. I'll just show you what exactly it is. I'll just draw a diagram, the load impedance, and I have that parallel stub. Note that it is not open. I have written short circuit. If I have closed that, it would be difficult to understand, so I just have put SCS there to indicate it's a short circuit. First step, as usual, normalize the load impedance, so it comes to 2 plus J2. I don't get confused, we'll go just step by step. What I've done is 2 plus J2, this point first. So I would request each one of you to go step by step. This is my first point. The first step I am doing is plotting my characteristic impedance on this Smith chart. Once I do that, for parallel stub, we know that it's easier to calculate parallel stub sums or parallel stub calculations if we have admittance. So how to draw admittance? From the center of Smith chart, draw a line across passing through the outer circle. Then take a compass, draw a VSWR circle with a radius as the center of Smith chart and the point of the normalized load impedance ZL part, which is 2 plus J2. Then once you do that, extend this line till across the whole Smith chart. The point at which the VSWR circle and this extended line intersects is the admittance of the normalized value. Once I do that, remember I am doing this because it's a parallel stub, and for parallel the calculation of admittance gets added, which is easier to calculate. Now how to find out the value of distance? As usual, the same step. I have here, you can see this point which intersects with z equals to 1, z equals to 1. Yes, here I have z equals. You might have imagined why didn't we write ZL, ZA1, ZA2? Because we are in parallel stub, we need to deal with YZ parameters. So this VSWR circle cuts 1 at here itself, so I'm marking 2 points, y1 and y2. Now I need to find out the value of it. So how should I find it out? Now I need to find the distance at which this stub would be placed. As we all know, the ZL is what is the point of consideration right now. Please don't get confused. We have just replaced or just converted ZL into YL because it's a parallel stub. So I need to calculate the distance from the load. So what I do is, as I told you in early video, that this is going towards generator, which is an easy step. So I'll be going from my load towards the generator. So this is my load, and if I move towards the generator, which is towards the generator, if I move in this direction, you can see here the nearest point is this and comes after this point, this YA2. Please don't get confused about the lines. Go step by step. First step, we plot ZL. Second step, we extended line. Third step, we draw VSWR circle. Fourth step, we mark the points at where the VSWR circle intersects with Z equals to 1 circle. Then right now the next step is I need to find the distance from ZL. I'm going towards generator. This is distance. So how I need to find out? It's a very big tedious task. No, it's damn easy. So what we are doing is, first we'll calculate this distance and then this distance. So out of 0.5, this is, you can see it's approximately 0.458. So out of 0.5 I am removing 4.8, so this distance remains, and I'll be adding in that this much distance, which is approximately 0.18. so you can see it's 0.5 minus 0.458 plus 0.18 lambda. 0.5 minus 0.5458 plus 0.18 lambda. Just don't get confused, people. So just put lambda outside. So what I get is 0.22 lambda. Now this is my, I got this is the place at which I need to have a stub. So but at this point I have a reactance, and the reactance value comes out to be 1.6. Now as I told you in the early video of series stub, if you are putting a stub, we need to see that we should get stable structures. For if we have impedance, we need to cancel it out. So what I'm doing is I have got J 1.6. After plotting, I'll just explain you. I have calculated distance, the nearest value should be the distance, and then I have marked this value, and then I have seen what reactance I get at the input of a stub, here. So as J2 has to be cancelled, for that here we have 1.6. 2 is of this, but we are considering this, the distance we have calculated 1.6. so I have marked first J minus 1.6. then from center I have drawn the circle, I'm sorry, from center I have drawn the line through the outer circle intersecting 1.6, because my reactance at the entrance or at the start or the Z-in of the impedance is plus J.6. I want to cancel that. For that I have chosen J minus 1.6. I have drawn it till the outer end. Now I should know that I need to go from here to short circuit, because it's a short circuit question, short circuit question. So in parallel we know that 0.25 is short circuit and 0 is open circuit. So 0.25 is short circuit, this is my open circuit. So I will be going from short circuit towards the ZN. So it's like going towards generator. So this is the distance, and I have to travel along the way till where the line which joins the center of Smith chart crossing through the 1.6 minus J 1.6 outer circle. So I need to find out this value. Is the length. So the length would be 0.25 minus 0.162. So this is 0.25, and remember, so I'm going from short circuit towards the load, so it's towards generator. So you can see this is 0.25, and the outer value is 0.338. So 0.338 minus 0.25, which is 0.08, so the length is 0.08. Again the same step, if you are given the operating frequency say 5 gigahertz, so my lambda is the standard value C by F. So we have the speed of flight as 10 to the power 8. I am assuming to be 5 gigahertz, which is 9. So it gives me 3 by 5 into 10 to the power minus 1, which is 6. So just put the value of 6, put the value of 6 here, and you will get the value of length. Save the value of distance. So what we should do if we get a parallel open circuit, if this becomes open circuit. Nothing to worry about, nothing to worry about. The distance what we calculated from the short circuit, we need to calculate from the open circuit. So I'll just write and give you, for open circuit the length would be, it is 0.5 at this point, as you know it's 0.5, and this is 0.34, it's like minus 0.34. so 0.5 minus 0.34 on calci I get, is it in lambdas? Just note that it is in lambdas, just forget to write here in lambdas, it's in lambdas. So the value comes out to be 0.16 lambda for open circuit. That's it. The difference between open circuit and short circuit only varies while calculating the length of the stub. Rest all the calculation remains. Just remember the golden rule. I will again show the golden rule for series stub. It is 0, it's short circuit, 0.25 open circuit, 0.25 short circuit, and 0 is open circuit. Thank you.